This week we are learning about atomic physics, nuclear physics, and the nuclear reactions that occur. First, a bit of review. You should have seen in the video already that there are two main parts of the atom, the nucleus and the electron cloud. There are two nucleons in the nucleus. Those are the protons. Protons are our positively charged subatomic particles, and the neutron, which has no net charge. Both of those have a mass of 1 AMU, meaning they have almost all the mass of the atom. The rest of the atom is made up of the electron cloud, which does have a negative charge. Electrons have a very tiny mass, but it is negligible. If we take a look at the periodic table, we can see there are many entries, and each entry has a couple of numbers as well as a symbol. This is the entry for helium. You can see the atomic symbol for helium is He. You can see the atomic number is 2 and the atomic mass is 4.003. The atomic number is the number of protons in the atom. If the atom is neutral, as in it's not an ion, that is also the number of electrons in that atom. The number of protons plus the number of neutrons makes up the atomic mass. Notice the atomic mass is an average. It's 4.003. That's because you take all the helium isotopes that exist in the world and you average their mass together and you come up with a non-even. There are different versions of an atom. If they have a positive or negative charge, they're called ions. And atoms that have a different atomic mass, but they're the same element, that's because they have different numbers of neutrons, those are called isotopes. And again, those are atoms of the same element that differ in their number of neutrons. A little bit more review. Isotopes of the same element have the same number of protons, right? But differ in their number of neutrons, which means they must have different atomic masses, right? What is the isotopic notation for C12 and C14? So this would be carbon 12 and carbon 14. Explain their similarities and differences. You can see here we have carbon with 6 as the atomic number and 12 as the atomic mass, and carbon with 6 as the atomic number and 14 as the atomic mass. Again, they have to have the same number of protons, the same atomic number, thus they are the same element, but they have different masses because they have different numbers of neutrons, and so their properties differ just slightly. Radioactive means that the element is unstable and tends to undergo decay. And finally, which elements have no stable isotopes? That would be anything the size of uranium or larger, with 92 neutrons or more. And that is simply because there the electromagnetic force is stronger than the strong nuclear force, simply because of the size of the nucleus, and thus we start to see atomic decay. Here's our atomic notation. Notice that we put the symbol of the element to the right, and on the bottom we put the atomic number, and on top the atomic mass. This will be the common way that we write out our isotopes when we're doing our nuclear math. So subtract the atomic number from the mass number to find the number of neutrons, right? So here we have a chart that shows us the number of protons versus number of neutrons in atoms. And you can see that this band represents stability. These are the stable elements. Notice that there is a balance between the number of neutrons and number of protons. If an element, or if an atom, an isotope, let me be specific, if an isotope has too many neutrons compared to its number of protons, then it tends to undergo beta decay. If it has too many protons relative to the number of neutrons, it tends to undergo positron decay, but we're not really going to learn about positron decay. If it's just extremely large, like it is uranium or larger, it tends to undergo alpha decay. And then in all sorts of radioactivity, gamma decay occurs as well. So if an atom is unstable, it is radioactive because it will tend to undergo radioactive decay. This is due to the number of protons versus the number of neutrons in that atom, as there is a balance between the strong nuclear force and the electromagnetic force that allows for those neutrons, those nuclei to remain. Let's talk about alpha decay. This occurs when you have a very large atom, something like bismuth or larger. These have tons of protons, 85, 95, 92 protons. These are very, very large atoms. And so what tends to happen over time is that the electromagnetic force ends up affecting that nucleus more than the strong nuclear force, and so you have alpha decay occur where a helium atom is released from the nucleus. What is a helium atom? It is 2 protons and 2 neutrons. 2 protons and 2 neutrons. So all we have to do to figure out what happens to this atom is take that uranium-238 and subtract 2 protons and 2 neutrons. So let's start with writing our uranium-238 out in atomic notation, with 92 on bottom as the atomic number, the 238 as the atomic mass on top. Now we can simply subtract 92 minus 2. We've removed 2 protons. 92 minus 2 leaves us with 90 protons. And now let's take the atomic mass. 238 minus 4, because the helium atom had 2 protons and 2 neutrons for a total atomic mass of 4. So 238 minus 4 leaves us with 234. So what we're left with is thorium-234. So alpha particles are not particularly dangerous if we do not breathe them or eat them. Alpha particles are released probably in your household. We'll talk about that in a second. What stops alpha particles are things like paper, skin, clothing, plastic, any real covering that you might have around something that released alpha particles generally absorbs or stops those particles. So when do we have to worry about alpha radiation? If it gets into the water or the food supply. That's when we've seen most dangerous results from alpha radiation. You don't want to get it into your bloodstream, because once it's there, it will tend to build up in the liver and it can kill you. But you don't have to worry about it in terms of getting, irradiated as you walk by your smoke detector. And that's where we see alpha radiation occur. In most smoke detectors, an alpha emitter is seated within that detector, and there's a receptor. And what the smoke detector is actually doing is reading whether it gets those radioactive alpha particles hitting it. If smoke gets between the radioactive source and the receiver, then it will block those alpha particles, and thus it will know that there's smoke in the house. If you have an atom where you have too many neutrons, this is a neutron heavy isotope, then that atom will tend to undergo beta decay. Beta decay occurs when a neutron turns into a proton. A neutron decays into a proton and releases an electron. So what is beta radiation? It's actually an electron. Let's see an example of beta radiation. If we have iodine-131, and iodine-131 undergoes beta radiation, we can see that the beta radiation particle is an electron, and we note it with an atomic number of -1. So let's do our same subtraction like we did with our alpha decay. We start with iodine 131 with 53 as our atomic number and 131 as our atomic mass. 53 minus -1 gives us 54. So all that happened to the iodine is by undergoing beta radiation, it released an electron and its atomic number went up by 1. The atomic mass didn't change because protons and neutrons have the same mass. So 53 became 54 and 131 stayed the same. It turned into xenon. A common place that beta radiation occurs is in carbon-14. Carbon-14, which is absorbed by living creatures, will break down, will decay into nitrogen-14 after that living creature dies. So, because we know the rate at which that carbon-14 decays, we can determine the age of formerly living things. Gamma decay occurs during other nuclear decay, or sometimes just as atoms become less energetic. You may remember from chemistry that atoms can become excited, and one of the ways that they can release energy is in the form of gamma radiation. This is a pure energy radiation. It doesn't change the number of protons or the number of neutrons in the atom, so there's no atomic, chain reaction that occurs due to the gamma decay, and there's no, math for us to do to figure out a new daughter atom. Gamma radiation can have extremely high energy, though. It can have energy high enough to kill life. It can cause changes to DNA. It can cause radiation sickness. And so it's very important to shield gamma radiation when it's in very high amounts. That being said, you are impacted by gamma radiation all the time. Granite and a lot of other rocks release gamma radiation regularly. So if you have granite countertops in your house, you're consistently exposed to small amounts of gamma radiation. Unless you are experiencing nausea, vomiting, and your hair is falling out, then you probably don't have radiation sickness from that. It's a very small amount. So it's important to know that radiation is around you all the time. It's part of the background radiation of living on this earth. It's really the concentration of the radiation you have to worry about. And large amounts of gamma radiation are extremely dangerous. If, for example, we had a pulsar collapse down and it released a beam of gamma radiation at the Earth, it could potentially kill all life on Earth. And of course, it'd move at the speed of light, so by the time we saw it, it'd already reach us. So that'd be a really unfortunate situation. This stuff happens in the universe all the time. We're just lucky it's not pointing at us most of the time, or any of the time so far. Anyway, so gamma radiation can be very dangerous, and so it's important to shield gamma radiation producers that produce large concentrations of gamma radiation. We can do this either with about a meter of water, or with a couple feet of concrete, or with a couple centimeters of lead or depleted uranium. Gamma radiation is used often in medicine. The idea of a gamma knife is to shoot gamma radiation in from multiple angles, and it will pass right through your body. But they have those different rays each meet up right on top of a tumor, and that causes that tumor to receive the gamma radiation from multiple directions. It creates a standing wave, which is something we'll talk about in a couple weeks, and that causes the damage to the tumor while passing through the rest of your body. So, in terms of penetrating power, alpha radiation is stopped by a couple sheets of paper. So you could actually, if you had to take apart your smoke detector, not that you should, because you don't want to get it on your fingers and eat it. But if for some reason you had to take apart a smoke detector, The alpha emitter could be safely stored by folding it up in a couple sheets of paper. Beta radiation tends to be stopped by aluminum foil or planks of wood or, a couple inches of water, um, bone. Beta radiation doesn't pass through semi-dense substances, and that's simply because it is now an electron rather than the alpha radiation which was this big fat helium atom, right? Helium atom can't fit through the paper. The electron can fit through the little gaps in the paper, but it can't fit through the thicker, denser substances such as aluminum foil. So, one of the ways that beta radiation is often stored is in folded up aluminum foil. People take aluminum foil, roll it up a little bit around the beta particle, the beta emitter, and it will not be able to emit outside of that envelope. Gamma radiation, like we talked about, tends to be stopped by either water or concrete or lead. So radiation is charged. Gamma radiation is not, but alpha particles are positively charged because they are two protons and two neutrons, and so they tend to be attracted to negative things. And beta radiation is negatively charged since they're electrons, and they tend to be attracted to positive things. Gamma radiation is not charged. Radioactivity can be measured using a Geiger counter. Geiger counters are those things you've seen in movies that go click, 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 and click at higher rates when they detect radiation. That's because they click every time that a particle hits them. So now we know the types of radioactive decay, but we need to learn about the rate of radioactive decay. And for that, we learn half-lives. Half-lives are the amount of time it takes for half of a sample to decay into a different element. So we can use half-lives to determine age of former living objects, like we talked about with carbon-14 dating. A longer half-life means it takes a lot longer for half of that substance to decay into something that is more stable. But short half-lives mean that that substance can decay very, very, very quickly. In fact, some of the elements that have been created in laboratories often have half-lives of milliseconds or even less, and so they decay very, very, very quickly. So half-life calculations are fairly straightforward. After every half-life, you have 50% or half of the element that you started with remaining. So after 2 half-lives, you'd have 25% left. 3 half-lives, 12 and a half or 1/8 the original amount, and so on and so on and so forth. The number never reaches zero. It's a horizontal asymptote, right? You are just decreasing by half at every half-life. So you can see, for example, on our chart, after 4 half-lives, you'll have 1/16 the amount you started with. Let's do a couple practice half-life problems. Number one, we have the half-life of radon 222 given to us is 3.8 days, and we know that we have 20 grams of radon in our basement. Hopefully not, as that is the second leading cause of lung cancer in the United States. Anyway, how much will remain after 19 days? Well, the first thing we need to figure out is how many half-lives have passed. To do that, we just take the total time that has elapsed, 19 days, and we divide by the half-life, 3.8. 19 divided by 3.8 says 5 half-lives have elapsed. Now we want to know how much is remaining. So at every half-life, we cut the amount that we have in half. So after the first half-life, we have 10 grams left. After the second half-life, 10 divided by 2 would be 5 grams left. 5 divided by 2 for the third half-life would be 2.5 grams left. For the fourth half-life, 2.5 divided by 2 is 1.25 grams left. And for the fifth half-life, 1.25 divided by 2 is 0.625 grams. That will be the amount left after 5 half-lives, which is 19 days. So a second problem, if we have 5 liters of neon 19 and it sits out for 103.2 seconds and the half-life is 17.2 seconds, what fraction of the sample is still remaining? What percentage? So let's start with figuring out how many half-lives have elapsed. To do that, we take 103.2 seconds and divide by 17.2 seconds. That means 6 half-lives have elapsed. Now, let's divide the original amount in half every half-life. So after the first half-life, we'll have half. After the second, we'll have a fourth, a third, the eighth, fourth, the 16th, fifth, the 32nd, and after the sixth, we'll have 1/64th left. That's the fraction of what we started with. Number 3, if the half-life of TC99 is 6 hours and 10 micrograms are left after 24 hours, how much was administered originally? So we need to figure out how many half-lives elapsed. So we're going to take 24 hours and divide by 6, and that means 4 half-lives have elapsed. So every half-life we divide by 2, right? But since we're going backwards, we're going to multiply by 2 for every half-life. So for that last half-life, we would have gone from 20 to 10. For the second to last, for the third one, we'd go from 40 to 20. For the second one, from 80 to 40. And that means for the first one, we started with 160. If an ancient scroll is discovered with 1/4 of the original amount of C14 in it, carbon-14, how old is the scroll? So the first thing we need to figure out is how many half-lives have elapsed. After the first half-life, we'd have 50% left, and after the second, we'd have 25% left. So it must be 2 half-lives. Now we just take the number of half-lives, 2, and multiply by the time of a half-life, 5,730 years, which gives us 11,460 years. And the last couple ideas for this unit include fission and fusion. Fission is the splitting of an atom. One way you can remember it is a fissure is a split between two things. So fission is the splitting of two atoms. Here we have uranium-235 being split by the insertion of a neutron. The way a fission reaction is begun is with the insertion of a neutron. A neutron is added onto that uranium-235 atom's nucleus, and that brings that nucleus above the critical mass. That's the mass at which fission can occur because it's just so large. So now that fission occurs, and during that fission process, 2 more neutrons are released from that fission process. Each of those is going to strike another uranium-235 atom, which is going to bring each of those above the critical mass, which causes each of those to go through fission, which makes them release, each of those release 2 more neutrons, which makes 4 more uranium-235 atoms achieve critical mass. This is called a nuclear chain reaction. And this is the way that nuclear bombs cause such large explosions and nuclear power plants create such large amounts of energy. These reactions have to be controlled when they're used for peaceful purposes, which is why there are control rods in all nuclear reactors. All nuclear power plants use fission reactions to generate electricity. The way this works is fission occurs in the reactor core, which then creates heat, which boils water, which creates steam, which turns a steam turbine, which generates electricity. These are closed loop systems, meaning the water that moves through the reactor is a separate loop than the steam that is generated. Therefore, if you ever see steam escaping from a nuclear plant, that can never, ever, ever be the steam or the water that moves through the reactor core, because those are 2 separate units. Fission reactors are controlled using control rods. Control rods absorb neutrons. Thus, if you think about it, fundamentally what control rods do is they absorb those neutrons that are causing the nuclear chain reaction. By absorbing the neutrons, other atoms are not being brought over that critical mass. So, in the United States, about 20% of our electricity is generated through nuclear fission. Could we generate more? Absolutely. Nuclear power is so much less expensive than fossil fuels, and it's so much safer, and it creates so much less radioactive um, issues. Coal burning creates so much radioactive sludge. I mean, on a order of magnitude, thousands of times larger than the amount of nuclear waste that would be produced using nuclear reactors. In addition, currently we can produce nuclear reactors that use nuclear waste to fuel their reactions. Why do we not? Because it's so expensive on the front end. As we can see in South Georgia, where we are currently adding in 2 new nuclear reactors. The other way that reactions can occur in the nucleus is through fusion. Fusion occurs where you have take 2 small atoms and press them together until they fuse into a larger atom. This is what occurs in the sun. And there are fusion reactors in the world. If we could ever figure out how to make them generate more power than they take to get started, then this would be the energy of the future. Right now, we spend very little money on researching fusion. But if we ever figured out how to make it work, this would power everything on Earth in the cleanest way possible. Finally, where does fusion occur mostly? Well, it's in the sun. It is the most common reaction in our solar system. Happens more than basically every other chemical reaction combined because it's occurring all the time in the vast majority of the mass of our solar system. So what happens? 2 hydrogen atoms are heated and pressed together enough that they fuse into a helium atom, and that releases energy. And that energy is what lights up our solar system, warms our planet, and keeps our plants and our seasons and our lives going.